Oops. Okay, good morning. All right, here we go. A second. So before we really get going today, well, first up, the lecture notes I'm going to be working off of is really just the back half of the notes that I posted for Wednesday. I kind of went overboard, so I won't be posting new notes. It's just the second half of the September 9th notes that are already on Canvas. The other thing that I want to say is that next week we are going to have our first exam. So on Friday, in class, we'll sit down, take a paper exam. We won't do any lecture. So some things to get ready for that. There'll be, well, this weekend I'll put up an announcement kind of laying out in more detail, but the exam is going to be covering all of the limit material and whatever we talk about today and Monday. So we might get into just the very beginning of the focusing on derivatives without using the limit definition every time. But what I also want to, so first let me take attendance here. What I also want to show is, some resources that are posted on Canvas that you can use. So one thing is that I posted a bunch of practice exams and other practice resources. So let me see. Okay. Oh, sorry, ONS here. Okay. So let me share my screen and just kind of walk you through some of those resources real quickly. So on our Canvas page, so the big one is Exam 1 practice materials. So the first thing is these first three are a couple, it says quiz. Well, I guess for all of these, ignore the names. These are old documents from previous versions of the class, but they're covering the right material for our class. So ignore the names. These two that are called quizzes, they're longer than the quizzes that we've been taking. They're for slightly different versions of the course. And so those have some problems along with solutions. There's a bunch of limit problems. If we actually pull this up, it's a lot of limits. If you're looking for some limit problems, here you go. And I also posted the answers. I don't have worked out solutions because, as you saw, that's a kind of a big list. But it does have all the answers there. And I'd be happy to talk about how, if you weren't sure how to get an answer, I'd be happy to talk about that in office hours, or I should say in lab next week. We aren't going to have a quiz. It'll really just be helping you review for the exam. So I might pick some of these materials and work through them, but ideally you would be doing some studying before that and then come to class and say, can we work out this problem? There are also 3 practice exams that are all a little bit different, but all covering the right kind of material. There aren't solutions to those just because I didn't write them up, but again, I'd be happy to talk about those answers in an office hour or in the lab session. Um, Beyond the exam one, practice materials, something I've been a little overdoing, but I'm caught up now. I have the lab quiz solutions. So here you can see actually not just those solutions to your problem or your quiz, but the solutions to all of the week's quizzes. The solutions from this week are going to be showing up soon. Certainly this weekend, if not today. And then as there always is, you can go back and look at the lab practice materials. So for this week, there's a couple quizzes from other versions of the calculus courses that I've taught, where you have the quiz document and then the corresponding solution. So there's a lot of practice material up here that I encourage you to look at. And if you have any questions, take advantage of the time slots, the office hour times that are set aside for us to talk, either on Zoom or you can come into my office. There's for one other person that we can talk there. And yeah, so those are all the exam materials that I wanted to point out. Okay. So then let's get back into what we were talking about last time. So the place that we had gotten to, well, we had first said that we'd been looking at this type of limit a bunch. And instead of saying this kind of limit, we give it a name, and this is the derivative limit. So this limit, the limit as x goes to a of f of x minus f of a over x minus a, which is the same as, or the same in that it gives you the same value when you compute it. It's equal to the limit as h goes to 0 of f of a plus h minus f of a over h. These two limits give you f prime of a, which is the derivative of the function f at the point a. So these two limits, if you choose an f and an a, give you a number if the limit exists. And today we'll get into situations where the limit might actually not exist. But another way of looking at this, instead of saying you have a function, pick a point, and talk about the derivative at that point, which gives you the slope of the tangent line at that point, we can say, think of this as a function where how do you tell what the function does? It says whatever x you pick, find this limit using that x. And so this f prime of x, the derivative of f, is a function that says, you give me an x, so we fix this function f. And what f prime does is say, you give me an input x, I will tell you an output, the slope of the tangent line of that function f at the point x that you chose. And how we find that is if we pick a function f. Here we don't have a specified point, but we use the same limit form, but we leave x as a variable in here. And so what happens if you compute this limit leaving x as a variable, there's a lot of the same steps going on. F of x, instead of being a number, is now a function. F of x plus h is you put x plus h into that function. We multiply things out. And some simplifying steps, which we saw every time we did this when we were getting specific slopes of the tangent line. Anything that doesn't have an h cancels. So these minus, so these x cubes cancel, these ones cancel, and then after you've canceled everything that doesn't have an h, then you can say this h on the bottom cancels with that h. There are two h's there. This 3 becomes a 2. And after canceling that h on the bottom, you get a limit that you can find by just evaluating. So you put in h equals 0, and we get 3x squared. But kind of the takeaway here is what this work has actually done for us is that if you start with this function f and you think about its graph, what this 3x squared is doing is saying you input an x into here, and the number you get will be the slope of the tangent line of this f of x at the x that you chose. So instead of having to do a limit every single time, this formula, so you do this limit once, leaving the x as a variable, now you can say, if you just put the x's in here, evaluate it, and that gives you whatever slope you want. So that's a recap of what we did last time, but questions about I guess the meaning of this 3x squared, or any of the process in finding this derivative. Okay. So let's try another example of this with some slightly different, kind of different looking function, and that will lead into some different behavior that will prompt some interesting questions. So let's find y prime for y equals the square root of x. So here, first up, the notation is a little bit different, but it's still saying your function is given by this equation, y equals stuff with x, and y prime is the derivative of the function that this equation is specifying. So while the notation is different, the limit that you find has the same form. So y prime, the derivative, is the limit of our function. And here I just kind of said, I am going to say that this is f of x. So this is the form of the derivative limit. And then we use our specific function, the square root of x. So we put x plus h into our square root to get the square root of x plus h. And then we subtract the function, which is the square root of x. So the first thing, and this works a little better if I'm actually writing it out, but there are really two steps here. Let's get a kind of fun thing. So we ignore this for a second. And as we're just trying to write down the limit, this is the limit which will give us the derivative. And as always, this is a indeterminate form. If you put in h equals 0, the bottom is 0, the top becomes square root of x minus square root of x, so that's also 0. And then what we have to do, and we did this in one example, if you look back in your notes computing, when we first talk about these indeterminate forms, if you have an 0 over 0 with these square roots, the way that we dealt with that is by revealing this thing that you can clearly see anyway. The way that we deal with this is look at this expression on the top and then multiply and divide by the version of this with a plus instead of a minus. So this first fraction is just what the limit we're actually trying to compute. But then we multiply and divide by the square root of x plus h plus the square root of x. Which, since we're multiplying and dividing, doesn't change the expression. But especially if you go back and look, if you find the example that we did earlier, there's a little more detail here. What happens is if you multiply these fractions across, on the bottom, you don't do anything. This kind of just carried around for a while. You just get h times this whole denominator. And because we're treating this as a single unit, I put it in parentheses here. On the top, what happens is there's a lot of simplification. And in particular, all of these square roots cancel. So for a little more detail, you can, we went through a few more steps when we did this example before, but basically what happens is if you're multiplying these together, you're foiling it, distributing everything. These two, when you multiply, give you the square root of x plus h, because you're multiplying something by itself and that cancels this square root. When you multiply these two together, you get minus you get this minus x because there's a negative, but the square roots cancel to give you just x. And then the big reason why this is especially nice is if you multiply these kind of cross terms, these two and these two, the inner two and the outer two, you get exactly the same thing. You have the same product, but one of them is negative. And so those outer term and inner terms, they cancel each other out and add up to 0, so those don't show up when we're done. So this multiplying by the conjugate is exactly the move that we need because we get rid of all the square roots. And then we can proceed with the simplification. So in these kinds of problems, we know what has to happen. We want to cancel as much as we can, with the eventual goal being this h on the bottom, we eventually want to cancel that somehow. And that's what we see happen. If we multiply this out, we get x plus h from these square root of x plus h's minus x from these square root of x's. And then x minus x gives us just h. And now we're set up to see the cancellation that you want to sort of keep your eye on the target for all of this work. This h over h cancels. And when you cancel, you also want to make sure that the top, so you still have a fraction, so there's this placeholder 1 on the top. On the bottom, you just have these square roots. But now this is the kind of limit you can find by evaluating. So if you put h equals 0 into this, you don't get 0 over 0 anymore. You get the square root of x plus the square root of x, which these are like terms, so you can add them together, and you get 2 times the square root of x in the denominator. Questions about this problem? And so again, what this really says is the square root of x that has some graph if you pick a point and say, what's the slope of the tangent line for the square root of x at the point that I chose, put that x into this formula, and that's the slope that you're looking for. One thing here, which is interesting and which didn't happen before, is if we look at the graph of this square root of x. Okay. And we think about the domain of these. So the function, if we look at, so what we did, the original function is the square root of x. The derivative is 1/2 square root of x. And then we think about what are the domains of these two functions. Well, the square root of x, you can't put negatives in, so that's from 0 to infinity, but 0 is fine. The square root of 0 is 0. For f prime of x, 1/2 square root of x, if we ask what the domain of this is, well, again, because there's a square root, we can't put in any negatives, but now 0 is a problem, not because of the square root, but because if you try to put in 0, the bottom of your fraction is 0, and that's undefined. And this actually matches, or we can see that this makes sense in another way if we look at the graph by saying, here's the square root of x. If you pick any point, you can draw its tangent lines. If you start drawing these tangent lines, and I can do a few in here, these tangent lines, imagine they're actually on the graph, but I moved them up for clarity. So if you draw these tangent lines, if you keep drawing them closer and closer to 0, they keep getting steeper. And actually, if you look right at 0, what it looks like is that the tangent line should actually be vertical, which is graphically something that makes sense. If you want to draw the line which is kind of in the direction of the graph there, it just hits that part of the graph at that point 0. But if you're thinking about the slope of a vertical line is undefined. If you pick 2 points on a vertical line, they have the same x coordinate. So the bottom of your slope formula is 0, and that's undefined. So graphically, we can see that the square root of x is defined as 0 and actually continuous at 0 if we want to use some of our other terminology. But the derivative doesn't make sense there. The derivative isn't defined there because the tangent line is vertical and there isn't a number which is the slope of that tangent line. Before we move on, questions about what I'm saying here? Okay. So this is getting to this, this is a place where we run into the fact that the derivative, and which is the slope of the tangent line, is defined as a limit, and limits don't always exist. So even though this function is defined at 0, the slope of the tangent line is not defined there. So this suggests that we have to think a little more carefully about when these slopes of the tangent line actually exist. What are other things that can happen? Or in what situations do we know that there are going to be, that functions will always have tangent lines? So before we get too far, we want to introduce a little bit of terminology. So first, say that a function is differentiable at a point if the derivative exists. So differentiable meaning able to be differentiated. So kind of the verb of what we're doing is to differentiate. The process of finding the derivative is called differentiation. So in order to find the derivative, you differentiate, and if you can find the derivative, it is differentiable. So these are the words that I'm going to be using, all just saying, when does this derivative limit actually exist? And so differentiable means, or differentiable at a point means the derivative at that point exists. And then like with continuity, we'll say you're differentiable on an interval if you're differentiable at every point of the interval. So given a function, you could ask, and there are 3 questions you can ask. What is the domain of the function? So where is it defined? Where is the function continuous? Which means where does the function value agree with the limit value? And then there's differentiable, which is when does the slope of the tangent line limit exist? And if you look in some of the practice exams, at least one version of them says, here's a graph, figure out what its domain is, where it's continuous, and where it's differentiable. And what you'll see is that you get different answers for them. So they're different properties that you're keeping track of. So, question, how can a function fail to be differentiable? What can happen so when you try to find the slope of the tangent line, you can't do it? So the first thing, and one idea which connects this new property of being differentiable to a previous property of being continuous, is that being differentiable is stronger. So if a function is differentiable, then the function is continuous. The way in which this is a little more usefully phrased is this kind of second equivalent version, which says if you have a function which is not continuous at a point, then the function isn't differentiable there either. And this version, I think, is easier to understand, because if you're not continuous, so that means that things like you have a jump, or there's a hole, or you have an asymptote. If you're not continuous, there's something wrong. Wrong is maybe not the correct word, but there's something complicated happening at A. And so if you're not continuous, how are you going to try to find the slope of the tangent line? So if your function has a jump, for instance, if your function looks something like this, you're not continuous here, you're definitely not going to be able to find the derivative. What would the tangent line look like? So what this says is, if we're talking about these properties of being continuous and differentiable, and also points being in the domain, if you find the domain first, any points not in the domain, your function isn't continuous there. And any point where your function is not continuous, those are also points where your function isn't differentiable. So the big question is, are there places where a function is continuous but not differentiable? And we have actually seen an example of that. That's actually the square root example here. At 0, the square root is continuous, but it's not differentiable. So this is a thing that can happen. The more general situation is we can get what's called a vertical tangent line. Okay. So graphically, what's happening is, well, there are a couple situations where you can have these vertical tangent lines. If you graph x to the 1/3, or this is the cube root of x, same thing, its graph looks something like this. It's like an x cubed, but turned on its side. And what happens is at this middle point, which is 0, if you actually graph it on an axis, as you're going from this bottom part up to this top part, in between, your tangent line is actually vertical. And like with the square root, if your tangent line is vertical, then the tangent line still makes sense graphically, but its slope doesn't make sense because vertical tangent lines don't have defined slopes. There's another picture that can happen, and that is, for instance, if you graph x to the 2/3. And here we get what is called a cusp. And if you graph this, it looks strange, but if you think about what is happening to the tangent lines, as you're moving in towards this point here, these tangent lines are getting steeper and steeper. And in fact, if you were at the bottom of this point and you tried to draw a tangent line, it would end up being vertical. And the same thing happens on the other side. As you draw these tangent lines, they get steeper and steeper. And as you're moving in, you end up having a tangent line that's vertical. So one thing that can happen is if the graph has a vertical tangent line anywhere, then you're not going to be differentiable there because tangent lines don't have defined slopes. Algebraically, what is happening is when you have a vertical tangent line, what's happening with the derivative is that the derivative actually has an asymptote there. So we haven't computed the derivatives of these two things yet, but we have talked about the square root, and we saw that there is a vertical tangent line for that. And we had seen graphically that square root of x has a vertical tangent line at 0. And if we think about f prime of x, 1/2 square root of x, yeah, at 0, this thing has a vertical asymptote, because if you put in 0, the form is 1/0, and that says you have an asymptote there. So that's one thing that can happen. These vertical tangent lines correspond to the derivatives, the derivative functions having vertical asymptotes. And so we can graphically tell, but also if we just have a formula, that's what you would look for to tell where is a function, where is this thing not differentiable. I should also specify the question of where is a function differentiable is exactly the same, or if you have a formula for the derivative, where is f differentiable is the same as where is f prime defined? What is the domain of f prime? And in this case, 0 is the problem point. We have an asymptote, but then we also want to think, if f prime has an asymptote, what does that mean about the original function? And what's happening is there's a vertical tangent line. Okay. Questions about this instance of how finding the derivative can go wrong? It's kind of the framing that we want to have for it. Okay. So another thing that can happen is, for instance, if we look at this absolute value function. So the absolute value is this piecewise function um, where it's x for things greater than or equal to 0, minus x for things less than 0. We get this nice V shape. Here we're not differentiable because we get it's sometimes called a corner. And one way to think about this is if you try to draw the tangent line, there isn't one. So in the above cases, the tangent line was vertical, but here there's kind of space for you to draw different tangent lines. And if you try to be as careful as possible, the issue is there are two good guesses. The left side, it looks like your tangent line should be this line. Line here going in the direction of the left half, but then the right side, it looks like the tangent line should be the line in the direction of the right half. And so it looks like there's more than one option for what the tangent line should be. And if there's more than one possibility, then, well, the derivative is a limit, and there's only one possible answer for a limit. So if it looks like there's more than one option, then we have to say, well, then the limit doesn't exist. So graphically, if there's kind of space, if there are options for what a tangent line could be, and you could even say something like, well, if I draw this kind of diagonal line here, this sort of fits the bill for what we want to be tangent. It just touches the graph at one point. And if there's more than one possibility, then the limit doesn't have a unique value. And so we say the limit doesn't exist and the function isn't differentiable. So this kind of corner is another graphical thing that you can look for where your function is continuous. So we know this is continuous, but it's not differentiable. It doesn't have a single number, which is the slope of the tangent line. We can also see what happens if we try to write down the limit. So maybe if somehow you didn't know what this graph looked like, you'd say, well, if I want to see if this function is differentiable at 0, this is the limit that I would write. This is the limit that you would try to find if you're looking for the slope of the tangent line. And if you simplify this, the absolute value of 0 is 0, so we don't have to write that. 0 plus h is just h, and the function is the absolute value. So the limit we're trying to find is the absolute value of h divided by h. This is something that we haven't exactly run into before, but what happens is because the absolute value is piecewise, this is a whole piecewise function, and we have to look and see what happens to the left and to the right. And if we look at those separately, say starting with the right, if we take the limit as h goes to 0 from the right of absolute value of h over h, how we proceed, because we'd like to cancel some h's, but if this h is stuck in the absolute value, we can't do it yet. The way that we proceed is we say, well, to the right of 0, which piece of the absolute value are we actually using? So this is like we had done with other piecewise functions. To the right of 0, we're in here, which means we're just taking whatever's inside the absolute value. So for positive h's, the absolute value of h is just h. And then after choosing which of the pieces we actually want, now we have h over h, that limit is 1, or that simplifies to 1, and the limit of 1 is 1. On the other side, if we approach 0 from the left of the absolute value of h over h, now what we're looking at is what is the absolute value doing if we're using negative numbers? And if we're negative, we are adding an extra minus sign to make u positive. So if we are looking to the left of 0, the absolute value of h is behaving like minus h. And here, after getting rid of the absolute values and choosing the right piece, now we can cancel again, but now there's an extra minus sign. And after canceling, we're left with a minus 1, and the limit of minus 1 is minus 1. So here what we see is that if this thing was going to be differentiable, we would find the slope we were looking for by finding this limit. But when we actually get down to try to find this limit using the tools that we've done before, we check the two sides, we get different answers. So this limit doesn't exist, which means this function doesn't have a derivative at 0. Questions about this that I can explain? Okay. So this is another point where a function can be continuous but not differentiable. So the limit is 0, the function value is 0, but we don't have a tangent line. But 0 is actually the only point. If you go greater than 0 or less than 0, the derivative to the right is 1 because you're on this line with slope 1. If you're to the left of 0 and pick a point, you're on this line with slope negative 1. And if you try to write down the derivative limit, there you wouldn't have to worry about the two sides because you're always using the same function value. You're always using the same piece of the absolute value around this point. Okay, so the kind of last conceptual idea that is a part of introducing the derivatives is what's called higher derivatives. So as we said, you have some function, you can find its derivative, which says for the f you started with, this function tells you all the slopes of the tangent line of that f. But you can say, well, you start with f, you differentiate to get a new function f prime. Well, this is a new function. Its graph has tangent lines. What are the slopes of the tangent line of that thing? And so you can take the derivative of the derivative, because this is just another function. It has tangent lines, they have slopes. What are they? And this gets into what are called higher derivatives. So if you take the derivative of the derivative, sometimes called the first derivative, just to emphasize that we've done this once. So the second derivative of f is the derivative of the derivative. The double prime, meaning you've done this differentiation process twice. Or y double prime. In this fractional notation, what happens is some 2's show up, indicating you've taken the derivative twice. Or in one of the other notations, what this last one says is that this expression, dy dx, this is the derivative. That is a notation for the derivative of y. And what you do is say, take the derivative again. That's what this expression outside is saying. Whatever is inside these parentheses, take its derivative. And what can happen is, if you can take the derivative twice, there's no reason to stop there. I mean, there might be reasons like, why is this useful? What information am I getting? But mathematically, there's no reason that you're unable to stop, unable to keep taking derivatives. So if you differentiated 3 times, then you would have f triple prime or y triple prime, or you would put 3's in this fractional notation saying that you've taken the derivative 3 times. Yes, and as always, this stuff is going to be on Canvas afterwards, so you can see it, and especially as you're preparing for the exam, you can come back and review all of this. All right. And you can actually take as many derivatives as you want. Kind of one of the last big topics of Calculus 2, you need to know every derivative for every natural number. So the first, second, third, fourth, fifth, sixth, and so on, all of them, you use them all. So there are kind of reasons why you would want to keep taking derivatives. But at some point, notationally, it gets difficult. The third derivative is maybe okay. If you wanted to write the 10th derivative, you'd have 10 of these check marks, and that's really hard to visually understand. So at about 3, you say, well, I'm going to put in parentheses how many derivatives I've taken. And the same thing for the y notation, y in parentheses, this isn't a power, so this isn't an exponent. If there are parentheses here, it's saying I've taken this many derivatives. And in the fractional notation, you just keep changing what number it is. So these higher derivatives, I said there's some mathematical use for them in Calculus 2, but especially the first 2 derivatives are really important if you're talking about physics. So an example that we had talked about was if your function is position, then the derivative is velocity. That's a connection that we'd established. But also, the second derivative is actually acceleration, because acceleration is how fast is your velocity changing. Velocity is the speed at which you're moving. If the speed at which you're moving is going up, then you're accelerating. And so the second derivative is the rate of change of velocity, which is acceleration. So the second derivative, acceleration is a huge part of force. So the second derivative is all over the place in physics. What's less common is the third derivative of position is what's called the jerk. It's really not that common. The place where it has kind of the most relevance is something like if you're shooting a rocket in the air and you are exiting orbit and an extra engine kicks in, that's a huge change in acceleration. That's where the jerk actually matters. At sort of normal human speeds, your acceleration doesn't change enough for the jerk to kind of do very much. Um, so where we're going to start next time, there's like 2 more pages of this kind of introduce, finishing up introducing the derivative. But what we really want to get to is finding these derivatives using limits is really cumbersome, and we don't want to keep doing it anymore. So that's where we eventually want to get to. How can we find some shorter ways of finding these derivatives? Okay. Um, so if there are any questions, I can stick around a little bit, but if not, have a good weekend, and I'll see you in person on Monday. Um, any questions that I can help with?